in the morning here and I'm still a little groggy, but thank you for inviting me to make this presentation. For many years, I've been very excited by the free energy principle and the great research being done by your group. I'm not an academic, but a layperson, and hope this different perspective will be of interest. The topic is the free energy principle and theories of everything, and we will explore some ideas on how the FEP might lead to a candidate theory of everything. First, a quick overview of the main topics we'll cover. We'll start with the relationship between scientific principles, theories, and laws. Next, we'll summarize the FEP with a focus on surprise reduction. Formally, surprise is the difference between model prediction and experience in reality, leading to the well-known deduction that this can be done in only two basic ways: either make the model closer to reality or make reality closer to the model. Then we'll examine some attempts at theories of everything, traditional attempts, and note criticisms of their usual reductionist approach. Finally, we'll discuss a possible solution based on the FEP. Okay, first, principle versus theory. Albert Einstein was brilliant about almost everything. Science, of course, but he also had deep insight into economics, religion, and philosophy, particularly the philosophy of science. In 1914, in an address to the Prussian Academy of Science, he defined scientific principle as a proposed scientific law that summarizes some general features of empirical facts. Principles hold logical implications of testable hypotheses that can be deduced, as he writes, inference upon inference, leading to the development of an explanatory theory. Testable hypotheses may be deduced from scientific principles, leading to scientific theories explaining why the phenomena occur. Principles can gain experimental support if the deduced phenomena are observed and if its explanation is informative to any existing well-tested theories explaining the same phenomena. Once the process theory explaining the operation of the principles have been extensively and successfully tested, they may become a candidate scientific theory or a scientific law. To sum up, the development of theories from principles. First, a principle is a precise formulation of a general feature concerning empirical facts. And a number of these testable hypotheses are inferred from principle that together may form a theory. And then experimental tests and agreement with any well-established scientific theories explaining the same phenomena determine the validity of the theory and therefore the principle. Einstein was keenly interested in the relationship between principle and theory because he considered the theory of special relativity to be based upon principles. Also, his principle of general relativity was principle-based. The two principles he based special relativity on were the speed of light is a constant for all observers, and also that the law of physics are invariant for all inertial observers, all observers traveling at constant speeds relative to each other. But these two principles cause a conceptual problem. They challenge our intuitive understanding based on the experience of only low-speed phenomena. If we are in a car traveling at 30 miles an hour and another car is approaching us at 30 miles an hour, we can say that the other car is approaching us at 60 miles an hour, the relative speed. The two velocities add. But if we are traveling at half the speed of light and an object approaches us at the speed of light, the constancy of the speed of light, the principle of the constancy of the speed of light for all observers, requires that we observe it to approach at the speed of light, not at 1.5 times the speed of light. When velocities are near the speed of light, they do not add. Low and high velocity observation thus seem to conflict. How can this be resolved? To understand how a theory accommodating both observations is deduced from this principle, let's consider the phenomena of a light pulse bouncing vertically between two mirrors, forming a clock that ticks each time the light reaches the top mirror. Let's also consider two observers, one stationary with its phenomena and one moving at a great speed horizontally to it. With this simple setup, we may infer through deduction a hypothesis of the theory of special relativity. The stationary observer observes a light traveling distance 2L in time 2L over c. The moving observer observes a light traveling distance 2d in time 2d over c. And we can see that 2d is obviously a longer distance than the 2L of the stationary observer. But given the constant speed of light, 2d over c is a longer time than 2L over c. The moving observer measures a longer time for the same phenomena than does the stationary observer. How much longer can be worked out using only a little math, providing a testable theoretic prediction. We have moved from principle to theory with only a simple mathematical deduction. Relativity isn't that difficult. The Lorentz factor, the denominator on the right, this relationship here, also affects lengths and masses. The theory of relativistic mechanics differs from Newtonian mechanics only by the application of this factor to times, lengths, and masses. But this transition from principle to theory faces further challenges. It must be compatible. It must be compatible with any existing well-tested theory. In 1905, very little was known about phenomena at ultra-high speeds, and the only existing theory that special relativity needed to explain was the Fitzgerald-Lorentz contraction, which it did perfectly. At low speeds, the Lorentz factor is extremely close to 1. If we can see from the, I guess it's obvious on the Lorentz factor that when V is close to C, the denominator is close to 0, and when V is close to 0 relative to C, the denominator is close to 1. So when at low speeds, we're just multiplied by 1 in Newtonian mechanics. And relativistic mechanics become identical to Newtonian mechanics, meaning that the evidence supporting Newtonian mechanics also supports relativistic mechanics. This compatibility test with existing knowledge poses a general challenge to the transition from principle to theory, especially so for a theory of everything. Oh, my slide isn't progressing here. Oh, here we go. Now let's consider the relationship between the FEP and established scientific theories, explaining the same phenomena. The free energy principle applies to everything and is not constrained to special circumstances such as high relative speeds. This is a great challenge. Theories inferred from it must be compatible with and inform much of our existing body of scientific knowledge. Carl's 2010 paper, The Free Energy Principle, A Unified Brain Theory, uses this method to argue for the validity of the free energy principle by interpreting numerous established theories and principles in terms of the FEP. The paper demonstrates that the FEP, applied to neuroscience, provides a framework capable of interpreting established neuroscientific theories. But the FEP is a universal principle applying to everything, and ultimately its supporting theory must be a theory of everything. a theory or framework capable of interpreting scientific knowledge of existing things. The free energy principle, which began as a principled account of neuroscience, may seem an unlikely basis for a theory of everything. All natural processes making their debut before the evolution of life are described by physics, which traditionally treats the subject matter in terms of inert matter. But these two papers interpret existing formulations of quantum mechanics, statistical mechanics, and classical mechanics in terms of inference in the FEP. As it has often been observed that the universe is quantum to its core, this is a revolutionary step towards extending the FEP towards a theory of everything. Biology is also included within the framework, as of course is neuroscience and culture. And by my reckoning, that covers pretty much the scope of scientific subject matter. And in that sense, it already forms a basis for a theory of everything. But uniting these separate subjects into a complete theory of everything might require identifying a single generic mechanistic process, and for that we might look again to the free energy principle. We will examine the free energy principle in a little more detail for possible deductions that might lead towards a universal theory. Wikipedia provides a good general statement of the FEP. The bolded phrases are particularly important to our account. We might take the first bolded phrase to say that the FEP explains the existence of all existing things. It is universal. The second phrase suggests existence is accomplished by minimizing the difference between entities' models for existence and their experience in reality. In other words, the surprise they experience. Given this interpretation, we might restate the free energy principle. All entities achieve existence by minimizing the difference between their knowledgeable model for achieving existence and their experience in achieving existence. This statement of the free energy principle stresses its role as a universal existential principle where all entities attempt to avoid surprise. Existence is accomplished and maintained by avoiding differences between models and reality, by avoiding surprises. Everything strives to avoid surprises, but this poor marmot has been surprised. It has tried to follow its knowledgeable model for maintaining existence, a model involving the detection and avoidance of foxes. But here it has been surprised and is in a state not predicted by its model. The odds of its continued existence are diminished. Good models for achieving existence must avoid surprise. The Wikipedia account states two well-known methods for surprise reduction: continually improving the world model and actively changing the world into states expected by its model. We might summarize these two methods even further. An existing entity can either make reality conform to its model, or it can make its model conform to reality. Free energy forms a bound on surprise, and that bound may be used as a proxy for surprise reduction. Formally, the expected free energy may be factored into epistemic value and extrinsic value, our two surprise reduction methods. Epistemic value has been characterized as a good scientist because the model is updated with the available evidence. On the other hand, extrinsic value has been characterized as a crooked scientist because it fabricates evidence in support of its model. The generative model of the crooked scientist engineers outcomes or evidence consistent with its model. A less pejorative term than crooked scientist might be good engineer, one that follows and uses the knowledge of its generative model to create existing entities. Together, they can form a synergistic relationship where the good scientist generates knowledge from evidence, and the good engineer generates evidence from knowledge. Now we'll take a quick look at theories of everything. Einstein was perhaps the first to seriously attempt one by trying to unite the electromagnetic force with gravitation. The electromagnetic force at the time was the only quantum force known, so it was an early attempt at quantum gravity. Over the past 70 years, other attempts have been made to unite the known forces and particles within a single theory, and this project has become the holy grail of physics. These theories usually concern phenomena at the bottom of the reductionist ladder, fundamental physical theories accounting for all fundamental forces and particles. Again, we can turn to Wikipedia for a description of this type of theory of everything. In short, traditionally theories of everything are physical theories trying to explain the very simplest components of reality. One line of criticism of this reductionist approach, outlined by George Ellis and others, is that while a complete theory of fundamental physics might give us a picture of bottom-up causation, or how everything is the result of fundamental forces and particles, this kind of theory cannot explain top-down causation. Judea Pearl, an architect of the causal revolution, describes some kinds of top-down causation as interventions undertaken by agents operating at a higher level than the cause phenomena. An example might be a scientist making interventions on a test group for comparisons to a control group not subject to those interventions. Another example is provided by biology, with genetic interventions causing biochemical pathways. In both examples, knowledge at a higher level intervenes in the normal course of events and causes outcomes that would not otherwise occur. In both examples, knowledge is fundamental to causation, and this may be difficult to incorporate into a reductionist theory of everything. David Deutsch, the Oxford physicist and founder of the theory of quantum computation, has identified knowledge as a fundamental physical principle and has placed it at the basis of his theory of everything, called constructor theory. According to Deutsch, constructor theory can incorporate into fundamental physics the fact that the most significant quantity affecting whether physical transformations happen or not is knowledge. Or as he wrote on another occasion, everything that is not forbidden by the laws of nature is achievable with the right knowledge. As an example of the fundamental role of knowledge in creating existing forms, we might consider that over its 14 billion years of evolutionary history, the universe has produced a relatively limited number, only about 500,000 inorganic chemical compounds, each composed of less than a few hundred atoms. While in a much shorter time, on one small planet, life's genetic knowledge has created about 19 million organic compounds, many composed of hundreds of thousands of atoms. This multitude of organic molecules is difficult to explain with a bottom-up theory. Left on its own, the universe wouldn't have produced most of them. They cannot be easily explained with a bottom-up theory in terms of fundamental forces and principles, or particles. They can be described in those terms, but their existence can't be explained. The laws of nature allow organic molecules, but they only came into existence when life evolved the knowledge to make them. Explaining the existence of most organic molecules requires a theory that encompasses the evolution of life's genetic knowledge. The point is that physical laws of nature make possible a nearly infinite number of things that could occur or evolve over the universe's history. But most of these possible transformations require specific knowledge, such as genetic knowledge, to occur. Thus, a theory of everything must account for knowledge that brings entities into existence, and it must account for the accumulation of knowledge for existing forms over evolutionary history. Knowledge is always hard won through evidence-based processes that a successful theory of everything must account for. The conception of a theory of everything as not only describing the fundamental building blocks of the universe, but also the knowledge transforming the building blocks into its observable structures, might seem to vastly increase the challenge. Not least among these challenges is the constraint formed by existing scientific knowledge. A successful theory must provide context and inform this knowledge. The free energy principle may be helpful as it describes the fundamental relationship between knowledge and causation. All entities achieve existence by minimizing the difference between their knowledge for achieving existence and their experience of achieving existence. How can we use this in constructing a candidate process theory of everything from the FEP? Perhaps we can start by noting the FEP's two processes for reducing surprise. The good scientist generates evidence from knowledge. The good engineer generates evidence from knowledge, and the good scientist generates knowledge from evidence. By themselves, these two methods are incomplete for our task. The good engineer by itself concretizes knowledge into physical existence, but begs the question of the source of that knowledge. The good scientist by itself updates the model to greater knowledge, but begs the question of where the evidence used in the update comes from. But together they may achieve synergy if the first step's missing knowledge is supplied by the second step, and the second step's missing evidence is supplied by the first. A straightforward method of constructing a candidate theory of everything from the free energy principle might be to synergistically join these two methods into a single cyclical process theory. This suggests a cyclical process. Each cycle of this process begins at the top with a generative or autopoietic model specifying an existing form. Autopoietic means self-creating and maintaining. It means self-evidencing, and the self part means a Markov blanket. We may refer to this model as a generalized genotype in analogy with biological genetic models. The right-hand arrow illustrates the autopoietic transformation of this model through the inferential abilities of the good engineer into an existing form, which we may typify as a generalized phenotype. Completing the cycle, the left-hand arrow illustrates the inferential abilities of the good scientist and using the entity's success in achieving an existence as evidence to update the generative model. Each cycle outputs both a new generation of generalized phenotype and an updated generative model. Importantly, in each cycle, the model at the end of the cycle is not the same as the model at the beginning of the cycle. It is updated to a greater probability of achieving existence. The process is evolutionary. For example, we might try to apply this candidate theory to biology, but biology already has numerous well-established process theories such as genetics, cell biology, and evolutionary biology. The first hurdle for using our theory as a biological explanation is to demonstrate its compatibility with these theories. We might identify the generative model at the beginning of the cycle as the organism's genome, a model well studied by the field of genetics. Genetics explains that encoded DNA is the knowledge directing the functioning of the cell and constructing multicellular organisms. The genome is a generative model as, in its role as the good engineer, it generates the phenotype from genetic knowledge. The transformation of this genetic model into a phenotype is described by the fields of developmental biology and cell biology. And finally, the updating of the genetic model using the existential experience of organisms, the good scientist in the process, is described by the fields of evolutionary biology and natural selection. Biology fits in a fairly straightforward manner into this theory, but any candidate theory of everything must accommodate more exotic branches of scientific knowledge, such as cosmology. Many advanced cosmological theories are based on string theory. The leading candidate physical theory of everything called quantum gravity that would incorporate all forces and particles into a single force and particle, suggesting in principle that everything is built from those forces and particles, the ultimate reductionist theory. But there may be more going on here than a universe built in a bottom-up manner from simple components. One of string theory's most exciting results is the holographic principle, and it conceives of the universe as emerging from an informational model, very much interpretable within our candidate theory. It views the universe as bounded by a generative model from which physical entities such as space-time, particles, and black holes emerge to form the physics of the enclosed volume. The algorithm forming the boundary is composed of entangled qubits, denoted in the diagram as conformal fields. So the diagram basically shows a boundary around the universe which has an informational model on it. The model is a conformal field theory. It can be considered written in qubits, and in the interior of the universe, we have the physical entities such as space-time, black holes, and the strings that make up in the theory all matter. And the interesting part, of course, is that it's speculated that the model causes the physics. In other words, the physics of the universe arises from the conformal fields, the algorithm on the boundary. This boundary forms a quantum algorithm specifying a quantum computation, and the output of that computation is the physics that occurs in the interior volume of the universe, called the bulk, containing physical entities such as space-time, black holes, superstrings. In other words, a quantum computation transforms a generative model into the physics occurring in the universe. As the army of scientific researchers and engineers attempting to implement quantum computation have found, their main challenge in building a quantum computer is error correction, or preserving quantum coherence until the computation completes. At least 90% of the qubits of a quantum computer are dedicated to error correction. Nature faces the same challenge, and much of physical reality, including four-dimensional space-time and gravity, is thought to serve as error correction mechanisms, allowing the computation coded on the boundary to complete. Our candidate theory can readily interpret this cosmological account of the transformation of an informational model on the boundary into the existing physical structures of the universe as the first step of his general two-steps process, generating evidence from knowledge. But what about the second step? How could the experience of physical entities within the bulk update the model on the boundary? How does this theory put its knowledge on an inferential basis? How does it generate knowledge from evidence? The quantum algorithm of entangled qubits forming the boundary is described mathematically as a quantum wave function from which predictions can be made of the outputs when the computation completes and decoheres. The quantum wave function evolves through time to predict physical properties such as position, spread out over a wide variety of possibilities. It makes only uncertain predictions. But when the computation completes, producing a physical outcome, and the entanglement decoheres, the wave function becomes sharp and now predicts this particular physical outcome with probability 1. In other words, in a Bayesian manner, the uncertain wave function receives information updating the model and reducing uncertainty. The model changes to stay in sync with the physical phenomena it describes. Perhaps in this manner, the quantum algorithm on the boundary evolves along with the physics in the bulk. In this manner, our candidate theory of everything interprets the field of cosmic holography. In its first step, the generative model on the boundary transforms into the physical universe as a good engineer, and in the second, the creation of the physical universe updates the generative model on the boundary as a good scientist. And so string theory, the ultimate reductionist theory, appears as anything but. Instead, it describes how the physical universe assembles under the orchestration of knowledgeable models and how the model accumulates knowledge through a Bayesian process, quite similar to biology. This analogy has been noted by experts in the field who describe the transformation of cosmological models into the physical universe as analogous to the transformation of genetic models into organisms. This analogy is conceptually central for some experts. They think that DNA is a very powerful analogy. It is remarkable that string theory, the ultimate reductionist theory attempting to explain everything in terms of a single particle and force building blocks, would find a strong analogy with the autopoietic aspect of biology, where a genetic model orchestrates particles and forces to form phenotypes. Evolving scientific knowledge has a way of diffusing strict dichotomies. For example, the great nature versus nurture debate has been subsumed into a single process employing both, where both are important and involved. Here we may be witnessing the same sort of diffusion of reductionism versus holism into a single process employing both, a physical theory where fundamental particles and forces are orchestrated by knowledgeable models. In this scenario, the cosmological model produces all the physical entities in the universe, including biological forms such as our cells. In that sense, existence is a self-similar structure where small-scale entities mirror the same structures and processes as the largest scale structures. This is similar to the FEP's Markov blanket approach, which reveals reality as Markov blankets all the way down. Loosely following the philosopher Auguste Comte, we may partition our scientific knowledge of reality into several domains: quantum physics, cosmology, biology, neural-based behavior, and culture. These domains each have distinct types of generative models, and each is perhaps readily interpreted by this candidate theory. My new book, The Knowing Universe, discusses each of these domains of reality within the context of the candidate theory proposed here. Thank you very much.
Thank you, John. Thank you so much. Before we move to the questions, can we please unmute our microphone and give him a round of applause?